If the universe truly has an edge, why does it keep expanding in every direction we look? For thousands of years, humans believed the cosmos had borders, a dome of stars, a final wall of light, a place where the sky must eventually stop. But today, with our most powerful instruments, the more carefully we look, the less certain that boundary becomes. We see farther than ever before, and still, nothing marks an ending. No wall, no rim, no cosmic cliff. So we are left with a deeper question, not just where the universe ends, but whether an end is even a meaningful idea at all. We know the universe is expanding, not as an explosion into empty space, but as space itself slowly stretching in every direction at once. When we look at distant galaxies, we see them moving away from us, their light elongated and reddened as it travels across the vast fabric of the cosmos. This is not a matter of perspective or motion through space. It is the geometry of space changing over time. We also know there is a fundamental limit to what we can observe. The universe has a finite age, and light travels at a finite speed. Because of this, there exists a cosmic horizon, a boundary defined not by matter or force, but by time itself. Beyond that horizon, light has simply not had enough time to reach us since the beginning of the universe. This boundary is real. Our instruments can measure it. Our equations can describe it. But it is not a physical edge. It is not a wall, a barrier, or an ending written into space. It is a limit imposed by observation, by the relationship between distance, time, and light. And that distinction matters profoundly, because a limit to what we can see is not the same as a limit to what exists. The observable universe is not the whole universe. It is only the portion of reality that has had time to reveal itself to us. Everything beyond that horizon may be just as real, just as structured, and just as vast. We simply have not seen it yet. If the universe truly has an edge, then logic suggests that position should matter. Observers closer to that boundary should see something different, a direction where space thins, where structure fades, where the expansion behaves unevenly. And yet, no matter where we look or where we imagine an observer might stand, the same pattern appears. Every observer sees distant galaxies moving away in all directions, as if they occupy the center of the expansion. This creates a profound tension. In an ordinary object, edges create asymmetry. One side ends, another continues. But the universe shows no such preference. No direction in space appears special. No region looks closer to a boundary than any other. The expansion is smooth, uniform, and indifferent to location. Even more puzzling is the large-scale order of the cosmos itself. If the observable universe is only a small portion of something larger, we might expect irregularities, differences in temperature, density, or structure caused by unknown conditions beyond our horizon. Instead, the universe appears astonishingly consistent. The same background glow, the same statistical patterns, the same balance, repeated across unimaginable distances. We know the observable universe has a boundary, defined by time and light, but the universe as a whole does not behave like something confined by an edge. It behaves like a system without a center, without a preferred direction, and without an obvious ending. This contradiction between what observation limits and what cosmic behavior suggests has unsettled cosmologists for decades and continues to challenge the way we think about space itself. The first possibility is, in many ways, the simplest and also the most unsettling to human intuition. The universe may have no edge at all, not because it stretches infinitely outward, but because it is finite in a form our everyday experience cannot easily imagine. It may close in on itself, much like the surface of a sphere. On a spherical surface, there is no boundary to reach. You can travel forward endlessly without encountering an edge, yet the surface itself is limited in size. There is no final wall, no abrupt ending, only continuous motion through a curved space that eventually brings you back to where you began. Applied to the universe, this idea suggests that space itself bends and reconnects, forming a self-contained whole. We know this much. Space can be curved. Einstein's theory of gravity allows it, and observations confirm that massive objects distort the geometry of space around them. But here is where the picture becomes uncertain. We have not yet detected the specific, large-scale curvature that would confirm the universe has this closed shape. Instead, measurements suggest something curious. On the largest scales we can observe, the universe appears almost perfectly flat. Almost, but not with enough certainty to rule out a subtle curvature beyond our current sensitivity. That narrow uncertainty leaves the door open. The universe may curve so gently that its true shape lies just beyond what we can presently measure, hidden in the limits of precision rather than in the absence of structure. Another possibility is more subtle and in some ways more frustrating. The universe may indeed have an edge, but that edge may be forever beyond our reach, not because it lies far away in ordinary space, but because the space between us and that boundary continues to grow. This does not violate the speed of light. No object is racing through space faster than physics allows. Instead, space itself is expanding, stretching the distances between regions of the cosmos. In this scenario, the edge is real. It exists as a physical boundary to the universe, but it recedes faster than light can carry information back to us. Any signal emitted from beyond that boundary, or even from the edge itself, would be endlessly delayed, never arriving within the lifetime of the universe. The boundary would remain real, yet permanently unreachable. We know one part of this picture with confidence. Cosmic expansion is accelerating. Distant galaxies are not merely moving away, their separation from us is increasing at an ever faster rate. But here, again, the pieces do not quite fit. If an edge exists, we would expect some trace of it, a preferred direction, a subtle distortion, a statistical imbalance in the structure of space. Instead, the universe shows no sign of proximity to a boundary. Expansion looks the same in every direction. The large-scale patterns of matter remain remarkably symmetric. If there is an edge, it leaves no imprint on what we can observe. It hides perfectly behind the rules of physics, revealing nothing and demanding that we accept the possibility of a real limit that can never be reached, seen, or tested directly. The third possibility challenges something more fundamental than distance or geometry. It challenges the meaning of the word universe itself. What we call the universe may not be the entirety of existence, but only a local region, a vast one, to be sure embedded within something far larger and more complex. In this view, reality is not a single, continuous expanse with one beginning and one boundary. Instead, it may consist of multiple cosmic regions, each unfolding in its own way. Each region could have its own expansion history, its own physical conditions, perhaps even its own versions of fundamental laws. Our universe would be one such region, a bubble of space and time growing within a broader cosmic structure. Seen this way, the edge of our universe is not the edge of everything. It is simply the boundary of our cosmic domain, the point beyond which our particular region of space no longer extends. Beyond it, other regions may exist, separated not by distance in the usual sense, but by conditions that prevent interaction. We know one thing supports this idea. The mathematics of modern physics allows such structures. The equations do not forbid them. But here, the tension returns. There is no confirmed evidence of interaction beyond our observable domain. No signal, no imprint, no disturbance that clearly points to another region beyond our own. The theory permits it. The mathematics remains consistent, but observation offers no reply. And so this hypothesis remains suspended between possibility and silence, a reminder that reality may be far larger than the names we give it, and that the absence of evidence does not always mean the absence of existence. One observation could change everything, not a dramatic image or a sudden discovery, but a careful measurement, quiet, precise, and unmistakable. A clear detection of the curvature of space itself would immediately reshape our understanding. It would tell us whether the universe bends back on itself, closes into a finite form, or extends outward without end. Such a result would not be philosophical. It would be mathematical, measurable, and decisive. Another possibility lies in the oldest light we can observe. The faint glow left over from the early universe carries subtle patterns, encoded at a time when space was young and structure was just beginning to form. A small irregularity in that ancient light, a deviation from perfect uniformity, could reveal whether our observable universe is part of a larger whole, or whether hidden boundaries influence its shape. A third path involves expansion itself. If the rate of cosmic expansion were found to vary in unexpected ways, breaking the deep symmetry we currently observe, it could point to conditions beyond our visible horizon. Even a slight deviation would carry enormous implications. Any one of these observations could tell us whether space curves back on itself, stretches endlessly, or conceals boundaries forever beyond reach. Until then, every hypothesis remains provisional. This is not a failure of science. It is how science advances by holding uncertainty with discipline, refining its questions, and waiting patiently for the universe to reveal what it is willing to show. If the universe truly has no edge, then a different question quietly emerges. Why does the idea of an ending feel so necessary to us? Why do human minds, shaped by beginnings and conclusions, keep searching for a final boundary in a reality that may not provide one? We know what we can observe. We can measure light, map galaxies, and trace the history of expansion across billions of years. But observation is not the same as existence. What we see is shaped by time, distance, and limitation. What exists may extend far beyond the reach of our instruments, untouched by our measurements and unnamed by our theories. The cosmos does not offer answers on human timescales. It does not explain itself quickly or clearly. Instead, it offers hints, faint patterns in ancient light, delicate symmetries written across immense distances, and long stretches of silence that refuse to be filled. That silence is not empty. It is instructive. Perhaps the edge we search for is not a place in space at all. Perhaps it is a reminder of proportion of how small a fraction of reality any single moment of knowledge can hold. Each discovery expands our understanding, but also reveals how much remains unseen. At deep space inquiry, we do not rush toward conclusions. We stay with the questions, allowing them to remain open long enough to matter. Because sometimes, the most honest truth the universe offers is not an answer, but the realization that mystery is not a failure of understanding. It is the horizon that keeps curiosity alive. The universe may never reveal where it ends, but in asking the question, we discover how far the human desire to understand is willing to go.